Hello, my name is Nathaniel Humanak. Thank you for attending my presentation on Copper Mountain Sandstone and the examination of equations of state and strength of quartz. Today, I would like to cover the properties of Copper Mountain Sandstone, starting with a brief overview. Then, onto the three main topics of study: the characterization of my material, a study of the minimum thickness required to study bulk material properties, and finally, the examination of sandstone strength under high strain rate pressure shear. Sandstone is a material of interest existing with high purities in a range of porosities. The abundance of SaO2 and the various forms in which it exists makes it an excellent material for study, being of interest to industry in everyday engineering. To describe properties of materials in continuum mechanics, we use the mass, momentum, and energy equations, closed with an equation of state and a yield model to describe elastic and plastic flow properties. We can find these properties through the use of experimental machines, such as tinsel testers and gas guns, which test for material properties at different strain rates. With these methods, I chose to investigate Copper Mountain Sandstone. The sandstone had a low porosity and had undergone diagenesis, making it a material which could stand machining and characterization without losing form. Machining was performed using diamond ceramic cutting tools, which were able to machine precise features into the sandstone. To characterize the morphology, a 2D section of sandstone was examined. This was later verified using a particle size analyzer. Additional bulk properties were derived, including density, porosity, chemical makeup, and crystallography, which revealed the sandstone to be primarily alpha quartz with 9% porosity. In order to compare Copper Mountain Sandstone at low strain rate, a literature-derived strength model for porous quartz was fit. Low strain rate testing revealed that this fit was also a good predictor of Copper Mountain Sandstone strength. Having characterized Copper Mountain Sandstone, it was necessary to determine the effects of minimizing sandstone thickness in the derivation of sandstone properties. Later strength measurements in Marquette's single-stage dual-diaphragm gas gun required as thin a sample as possible. Before characterizing Copper Mountain Sandstone, the equation of state properties of porous quartz were examined, and a P-lambda model equation of state was generated based on porosity and the properties of alpha quartz from 0 to 8 GPa. In experiments, sandstone samples of 1 to 2 millimeters thickness were impacted to determine at which point homogeneous heterogeneity could be assumed. It was expected that Copper Mountain Sandstone would behave similarly to nugget sandstone, shown here in red. As samples were cut thinner, they tended to have greater porosity and behaved according to other, more porous sandstones. Based on this information, work proceeded on characterizing sandstone strength under pressure shear at high strain rate. Because of the rather large 2 mm sandstone thickness required, samples could only be brought to approximately 90% of pressure equilibrium before shear was applied. Results of these tests showed the ability of Copper Mountain Sandstone to carry an input state of loading, thus describing its yield surface. In particular, it was noted that sandstone at similar strain rate was stronger than sand, and that, as the sandstone densified, it had strength properties on the order of that of the low strain rate data. Finally, I would be remiss in not acknowledging the vast number of experts I was able to consult over the course of this study. Thank you.